I'm going to talk to you about language, DNA, and thermodynamics. So it's quite involved. It's not the faint-hearted, and I don't apologise for that. But in applying thermodynamics to DNA systems, we had a great talk in the Science Network from Peter Borgen earlier on the fact that information is far more than just but it certainly is there in DNA. But we had a lot more than that Peter was showing to us, the non-material aspect of information in terms of language. So this overlaps that whole matter, but I'm coming at it from a thermodynamics physics background. I've already published this chart, and you'll have seen it in some of my papers. If you go to the paper which was published in the BINP, Biological Information volume in about 2013, you'll see that paper, and also it appears in a Design in Nature paper. Basically, information is non-material is really the position I'm taking. But I want to show you how that really fits with the science. The evolutionary view, of course, says that matter and energy left long enough will actually produce the DNA coding, but all the other information systems, which are locked into the nucleotides of DNA and many other systems, which some of us were hearing about, not all of you here, but those in the Science Network heard this morning. So that really is the issue. Is it a bottom-up view or is it a top-down view when we consider what is going on in the physics of the DNA system and the information that is there? There are laws of thermodynamics. I don't want to burden you too much with these laws. There won't be a test afterwards. But if you really want to get involved in this subject, you've got to know what's gone on before. And the first law of thermodynamics says that the total amount of energy in a given system is conserved. Energy is neither created nor destroyed. The second law always trips people up. It says that in an isolated system, the amount of energy that cannot be used to do work is always increasing. In other words, there's always an energy loss per degree. We call that entropy. So the entropy generated, we use S for entropy, is always greater than zero in an isolated system. And the entropy, as I've said, is the energy loss per degree. So basically that law says that there is an arrow of time going on in all systems. There is an arrow of time which you cannot ignore. There is a direction in which the physics is going. Now, this is, thank you very much indeed, Connie. This is something which I've spoken on before, so I'm not going to say too much on this here. I've developed this point in the papers that I've produced, and I've actually done a talk here some years ago on this issue as to what happens in non-isolated systems, right? But just to remind you, if you've not come across this, that a number of us have worked on the thermodynamics of non-isolated systems. Indeed, it all began when a certain gentleman from Oxford by the name of Dawkins challenged me on one occasion to say there's lots of energy out there to build systems. He was trying to appeal to the fact that the sun, basically, is going to have the capacity, once you zap something with energy, to produce all the information systems and all the energy control systems that are going on in living systems such as ourselves and the plants and everything living. So he was proposing that essentially entropy will decrease and the amount of energy available to do useful work will increase if we just zap with a lot of sunlight and radiation, cosmic radiation even, that will do it. But is that really true? And if you refer back to some of my papers, you'll see this argued much more robustly than I'm trying to summarize it now, because I want to get to some things which are perhaps a little bit not so well known. This bit is known now and is in the literature. But just to show you what really this implies, it's all very well saying that a living leaf, and there are literally trillions of them, all around here in Silesia, beautiful sunlight, doing this photosynthesis. But what is happening thermodynamically with leaves? Well, the energy is coming in onto the leaf, onto the surface of the leaf, of the chlorophyll, is causing an incredible reaction to take place where the energy, due to the catalytic effect of the chlorophyll, is going down very specific pathways to eventually produce sugars, which we all love, and plants definitely love the sugars. And the sugars then, of course, give them energy, and the byproduct of that is that we get oxygen as the carbon dioxide is taken in to produce the sugar. But if that leaf was dead and we had the same effect going on, would it do anything? And the answer is zilch. Absolutely nothing. In fact, if you had a dead stick or a dead leaf, all that happens is that it just heats up. The energy, yes, comes in, but it doesn't do anything except just heat up that which is there, which is why plants, of course, are slightly cooler in terms of their leaves. If you touch the leaf of a plant, you know it's real, partly from the temperature as well as, of course, the texture. There is a slight drop from the environment because some of the energy is being used in a very specific chemical pathway to produce the sugars. So just to give you all the reaction here, if you really want to know, chlorophyll is on both sides of that diagram, and some of the water is actually being used in order to produce sugar and oxygen, which is very useful. This photosynthesis is an incredibly, I won't go into the detail, but it's a very, very complicated reaction. And it's not actually as simple as even that line with the chemistry in suggests. It's a whole series of reactions, which I've just summarized as one overall reaction there. The chemistry is incredibly complicated indeed. So, but that just gives you an overview of the thermodynamics. So, was my colleague from Oxford correct when he said that to me? No, he was totally wrong. He hadn't understood the thermodynamics of not just closed systems or isolated systems, but in this case we're talking about open systems. And he hadn't understood thermodynamics 101. So he needs to go back and go over that work because it's hugely relevant to living systems, which then led to suggesting basically a thermodynamic principle. I wouldn't be so bold as to call it a law, but it's certainly an additional thermodynamic principle which applies to non-isolated systems. And the principle would go like this. In a non-isolated system, the free energy, what is that? Well, I'll give you a better, perhaps, understanding of that in a minute. But the free energy means the energy available to do specific work, right? So it's really all the energy available minus any entropy terms, which are always going to be there in any real system. So that's what we call the free energy. The technical term is Gibbs free energy. In a non-isolated system, the free energy potential will never be greater than the total of that which was already initially in the isolated system, and that coming in through the boundary. So free energy, as I've said there, you can loosely regard as the energy which is available to do work. It's the overall enthalpy, that means the total amount of energy available per degree, total amount of energy, enthalpy, it's actually a unit of energy, minus the entropic term, which would have to be written as entropy times the temperature. So that's basically the principle that's involved. So in mathematical terms, that's what free energy is. It's the overall enthalpy minus the entropy term. And that, I'm proposing, the free energy potential will never be greater than the total of that which was already there, plus any which may be coming through the boundary. But it cannot just be a random energy. Random energy coming through the boundary will do zilch. You've actually got to have some very specific energy pathway system already there in order to do anything useful. Random energy, another way of putting this, does not build machines. And I'm using the term machine, so I want to define it. I don't mean nuts and bolts machines. What do I mean by the term machine? Well, I'm going to use the term machine to mean anything which locally raises the energy able to do work. It could be a battery, which doesn't immediately get its energy used, but it has the potential to do something very useful with electricity, particularly if it's the right size and can actually fit into some device that I have, right? Or it could be that it immediately does some work. So this is the principle that I'm getting at here, that the free energy potential is never greater than the total of that which was there already, plus that coming through the boundary. In other words, how would it come through the boundary? Here, guys, here's a battery for your system, or here's a solar cell, which could take the random energy and make it do something useful, like produce electricity to power your washing machine or whatever it is that you want to do, right? But of course, a leaf is effectively, in my definition that I've just been using, a machine. I don't mean engineering nuts and bolts motor car. I mean something which has the potential to take random energy and to convert it, once the random energy is available, into yum sugars, which the plant can use, right? That's probably made your head hurt, but let's just give you some illustrations, right? Because most people get lost with this, and I'm aware of this point. I've tried to even talk with engineers, and they get lost. So if engineers get lost, right, some of you who are not engineers but have come from other disciplines will get lost. So I'm going to use some illustrations to help you to understand. Here's a picture of the Austrian dam called the Kilnbrine Dam. I probably pronounced it incorrectly. Forgive me if I haven't. But doesn't matter which dam it is. But a dam, it's got a huge amount of water behind it, all ready to do what? To drive a turbine, usually to convert to electricity. We have them in Scotland. Lots of dams, we have a few in other places as well. It's basically a machine. A hydroelectric dam is a very good illustration of this principle. Raw energy, right? Not in this case, not from the sun. This is raw energy from a river flowing, right? Is harnessed, ready to do something useful, right? So remember I said you could have a battery. I'm going to mention batteries in a moment in living systems. So it's harnessing the random effects of water flowing and say, no, you're not going to go down that random pathway that just cuts through the forest or whatever. You're damming the river and saying, we are going to control when that flows, and we're going to have it flow through a water turbine to produce electric energy. Now, if you look at the paragraph at the bottom, it says, in living systems, energonic reactions, I'll explain that word in a moment, are used and enabled by other molecular machines. What do I mean, endogenic? Well, we could put there endothermic. Again, you probably don't know what that word means. Endothermic means that which takes in energy as the reaction progresses, chemical reaction. Exothermic, or sometimes called exogenic, is the opposite. It means it gives off energy as the reaction progresses. Now, there is a host of chemical systems in living systems which actually need energy. They suck energy in. And if you don't have that capability, they're not going to work. But ATP, which is a very important molecule, without which nothing will work whatsoever. We'll all be dead immediately if ATP is not working, right? ATP synthase, I should say. ATP synthase produces ATP, which is a high-level energy molecule which very quickly wants to dissipate its energy, right? So ATP synthase, we could do a whole talk on ATP synthase, which is actually an incredibly sophisticated machine, actually. But I'm not going to go, I'm tempted to go down that little bypass, but I'm not going to do it. But just for a moment, just to make it plain to you that ATP synthase is a very, very important molecule, which makes adenosine triphosphate, which is a very high energy molecule, which very quickly wants to get rid of its energy, right? And it's got to have a very specific system in order to do it. But now, let me now point out to you that, actually, you've got to have a very specific energy pathway to get this system to work. Life is full of systems which need to have energy, right? So ATP synthase that I mentioned makes ATP. Now we're going to refer to a paradox that's going on in living systems. Because remember, I also said that living systems have flat batteries, which are going to be referred to in this next little clip. They are called adenosine diphosphate, which does nothing, but is going to be actually made into adenosine triphosphate, which is like a charged battery. So this little clip is commenting on that dilemma. Let me play it to you. So there is a paradox of ADP, the flat battery, ATP, the charged battery, and ATP synthase, which is the machine, which actually, in order to work, needs, would you believe it, ATP. So we're going to see a real paradox in this. So that is a huge problem. The whole system, yes, is going to use raw energy, but you've got to have this very complicated system ready to use it. And indeed, I haven't mentioned it, or at least that video doesn't mention it, but ATP synthase is used in a whole vast set of machines. I haven't played you a video that I've got of kinesin, the walking molecule, which is a cargo molecule which needs energy. Where does it get it from? It actually uses ATP, but so does polymerizing DNA in order to polymerize it and to add other links to this huge long molecule. The vertical strands will actually have ATP come along, give off the energy in order to make those linkages work. So you're back to this issue of the fact that you've got what's called endogenic reactions. In fact, the free energy problem you could summarize like this. You want to go to a finishing line where the energy is raised. In fact, you can't do it because there is no system immediately to make the links come together, or the nucleotides, bonds as well on the horizontal rungs of the ladder, as it were, of DNA. Think of that DNA molecule. There isn't any way to make them join together at the vertical strands, so you have to bring ATP along to do it. You may have all the bits to actually make that molecule, but you've got to actually have an energy molecule come in order to do it. You're actually putting energy into the system. And then, normally, you actually have reactions going on naturally, which are exothermic. So how do you go from a start to a finish where the energy is actually raised? Well, you actually have to have an energized intermediate, which is where the ATP comes in. So in making DNA, I'm just using that as an illustration here. You've got the raw building blocks. You've got a free energy change, which is positive, which just will not work naturally. But if you have an energized building block, which is ATP, then you can make it work, which is what's being done when you polymerize DNA. So there is a free energy problem in living systems. That's really been the whole point of the last few minutes of what I've been saying. Well, if you thought that was bad enough, now I'm going to come to the issue of information. Yes, your head hurts, but now I'm connecting it with information. You're perhaps familiar with, I'm going to just summarize the issue of digital information systems. It's much more complicated than this diagram suggests, but you perhaps know that it's actually the letters and the orders of cytosine, adenosine, and thymine, which stands for the information to make one amino acid, or cytosine, thymine would refer to a different amino acid. There is a massive amount of biochemistry involved. It's nowhere near as simple as that, but this just summarizes the system that we have in DNA. And we have Peter Borger here, who's an expert, and I'm not a biochemist, and I don't claim to be. But I do understand the issue of information. Interestingly, those who are not Christians, like this gentleman, he's died now some years ago, these people admitted, he admitted at least, and some admit, that there is a big issue, as we were hearing in the Science Network today, concerning information. Information doesn't have mass or charge or length in millimeters. Likewise, matter doesn't have bytes. You can't measure so much gold in so many bytes of information. It doesn't have redundancy or fidelity or any of the other descriptors that we apply to information. The dearth of shared descriptors between matter and information makes for a big problem. They are two separate domains of existence, which have to be discussed separately in their own terms. Now, I think things have moved on a bit since that statement, but essentially he was right. There was a lack of ability to communicate the two issues. Computer scientists know full well that information is to do with software, which cannot be defined by the hardware. That's another way of putting the same point. So we're back to this diagram that I showed you earlier. So this diagram. And as I said, a lot of this is discussed, so I won't go over it all again in my paper, Information and Entropy, Journal of Design and Nature, 2009. That was some years ago. And then there was a second paper, Information and Thermodynamics in Living Systems, which is 2013, which is still some while ago. Now, this next part that I'm going to talk about is where really I wanted to get to, because I presented this in the International Conference on Creation last year, and it is published in the proceedings of the ICC 2023, this next bit. And I must acknowledge my good friend Salvador Cordova, who's actually one of the brightest people on the planet when it comes to this issue of understanding thermodynamics and information. He's done a lot of biochemistry as well as physics. He and I had a discussion some while ago where the bright box that he is, he said, had you thought about the Landau principle? let me discuss with you what the Landau principle is. Rolf William Landau died in 1999, but he was the one who has the credit for postulating that there is a minimum amount of energy, which is kT log 2 joules. It's not a very big amount of energy in our terms. You won't be able to light a match with it, but it is nevertheless a real amount of energy. He postulated that there is that amount of energy. K is the Boltzmann constant, T is the temperature, log 2 is what it is, okay? And that amount of energy is associated with the erasure of 1 bit of information. This is approximately 3 times 10 to the minus 21 joules. I told you it wasn't very much, right? But it is nevertheless a finite amount of energy for a room temperature. That is, if T is 300 K, that's what it comes to. K is Boltzmann constant. So information has an energy cost. Any logically irreversible transformation of information. What do I mean by that? Well, that means when the output is such that the input cannot be determined from that output, right? So there is you cannot deduce where that information has come from, is necessarily accompanied by that amount of joules of heat per lost, that should say per lost bit of energy. The amount of heat energy lost per bit. So, the opposite situation of storage of information then leads to an assertion that at least a free energy requirement of kT log 2 joules is needed to locally establish 1 bit of information on a substrate. Now, this is getting complicated. I told you it would be. And I make no apology. But this is basically saying that if you've got some information, it's going to require some energy input to put it there. Remember I said that the DNA, you have to put energy in to make that polymerize. It won't polymerize on its own. Indeed, if you see a dead person, you'll notice that eventually, it's not very nice, is it? But you know this, that we basically disintegrate. Our cells disintegrate. The DNA, after quite a long time, it can actually last quite a fair time, but it will eventually disintegrate. So it's hardly surprising that in order to keep your DNA going in the system, you've got to have ATP synthase whirring around in order to produce ATP, in order to make other bits of DNA. That's going on all the time as we're living. But eventually, we'll die. So that's the basic point that I'm making. In order to keep living systems alive, you've got to have that information system I'm talking about, the substrate of DNA, actually going with its energy input. This is what I'm now going to apply Landau's thinking and my postulate here, right? So that's a postulate that I'm making. Now, Landau's postulate was eventually proved. It was a very complicated reaction done, complicated experiment done involving, it involved an energy potential well, and when the electron, or the sort of silica beam, not an electron, it wasn't as small as that, you could have done it with an electron, but they did have a very, very small silica beam, 2 microns, right? And they noticed that when you actually caused it to move from one potential well to another, there was a very specific amount of energy, and it was actually linked to Landau's postulate. It proved it, and there's been other experiments since. If you don't mind, I'm going to skip the next bit, because actually there are implications on cognition and knowing anything, which there is a philosophical implication with Landau's postulate, which I won't go into now. It's a very interesting connection. But to know anything requires energy. And frankly, that is a very interesting point. Let me, though, jump to the point that I really want to get to. I looked at the energy bonds in a typical strand, or just a tiny little strand, actually, not the typical strand at all. But I was reading the papers on energy bonds in the triplets of nucleotides. So, if you like, I could have taken some of the work that others have done here on DNA and actually looked at the energy bonds of any strand of DNA. This was from a paper by Volker and Klump and others, and it's the energy mapping of the genetic code and the genomic, and then it talks about the implications of those energy bonds. So what I've done is I've taken their paper. They weren't actually using joules. I've converted what was, I think, calories into joules. And this is in kilojoules per triplet. And you'll notice that this is triplets, right? So you've got the first part of the first bond, if you like, the nucleotide bond, the thymine. Then if the next one is thymine, you go to the first top left, right? And then if you're going to actually go to cytosine, right, it would be the second one down. And then that codes for a particular amino acid, which is PHE, and it's all listed down there at the bottom as to what each of those amino acids are. So I was just going for TTC. It may not actually be one, but I know that CTT is. So if you go for C and then T, that takes you to the second block of 4. Then you go for T on the end and you come to 15.5. You get the general idea from here. So if I now put that up on the top right, the lowest free energy of the table is that required for stabilizing ATA and TAT, both of which are 11.7 kilojoules per mole per triplet, which translates to approximately 19.5 times 10 to the minus 21 joules per triplet. And this is where it gets very interesting. It's approximately 6.5 times the Landau limit for a bit of information. And actually, when I talked again with Salvador Cordova, he made a very interesting observation that the number of possibilities for a triplet is in fact 6 possibilities. This is 3 times 2 times 1. And so this is incredibly close to the actual Landau limit for one of the triplets, or one of the components rather of the triplet. So it's 19.4 times 10 to the minus 21 per triplet, but it's actually very close to the 6 times 10 to the minus 21 per bit. So it's actually, you've basically got in a triplet 6 potential bits of information. So this means that the DNA is operating incredibly efficiently. There is a minimum which Landau suggested, and it got proved. But when you look at the DNA is almost at the minimum. Not quite, because some of them are higher than this. I was going for the lowest, and if you go through it, then they're always going to be a measure slightly above or getting very close to that limit itself. But I need to close. But I'm going to close at this point rather than trying to say more, because I want to give you a chance just to talk back to me. And I think if you ask some questions more on a particular topic, I may put something in just to help for you to see what I'm doing with this. But I would just put up this quote that, of course, I haven't really dealt with the issue which, for those of us who were here this morning at the Science Network, Peter was addressing, which is, of course, this could be any old junk, right? Well, actually, the DNA is shown not to have junk in it, but it could be proposed that it doesn't matter what you do with these nucleotides. You're always going to have this issue, even if you try to put junk in there. Well, I realize that, and that one does need to know that, as was mentioned this morning, that there are levels of information which Werner Gitt wrote of in his book. In the beginning was information, and two of the five that he refers to in his book, is that you've got to have a language which can use that coded information, and you then got to have a meaning to that language of words that you're using. So there is buried in the DNA communication system the whole issue of message, which is using the DNA code. And the quote that I just want to give to you is from another gentleman who's worked in this area. And that is John Baumgartner, who gave a talk back in July of it was 2022, I think he gave this. He gave a talk on what is language, and he made a very interesting point here. What is language? Language is simply encoded meaning. How is meaning encoded? First, small snippets of meaning are assigned to a set of tokens or symbols, which we usually refer to as words. The resulting set of words forms what is usually referred to as the vocabulary. Second, a set of rules, usually referred to as the grammar, is specified by which elements from the vocabulary may be joined together to create more complex meaning structures. Language is a non-material reality. Because meaning is abstract and non-material, so is language. Language is merely encoded meaning. This is why the meaning of a linguistic message why the meaning that a linguistic message conveys does not depend on its material carrier. A message, if reliably encoded and transmitted, is the same whether it is via paper, ink, or a magnetic disc, or a plastic CD, or chiseled on a rock. Meaning is independent of matter. A linguistic message then reliably transmitted is identical whether it is carried by acoustic waves through the air, relayed electronically, faxed, emailed, encrypted, sent through the mail on a DVD, or carried via smoke signals. The message has an identity and a reality independent of its material character. So I find that actually very powerful, that statement. It's an assertion, I grant you, but it fits the evidence. So my conclusions: information is indeed non-material. It sits on matter and energy and uses it, but is not defined by it. It connects with matter and functions even at molecular level. There are principles of information exchange, which I haven't been able to develop in this talk because I couldn't do everything. You'd have to refer back to my papers on that. There is a minimum energy cost per bit of information stored in DNA, and it is close to the Landau limit. I'd like to put this verse in closing. There is a verse in the scripture which says, "In him we live and move and have our being." I believe that's not just true in the sort of philosophical realm. It's not just true in the spiritual realm. It's true in the physical realm, because who is the one who has organized a system such that all these raised free energies are exactly right for the DNA system to work? Who is the one who has put all that machinery in order to sustain life? Well, it's none other than God himself, which is why Kepler said that he felt that he was thinking God's thoughts after him as he made his discoveries of the planets in his work. But it's true even of the biologists and biochemists today. Thank you.